Hi, good afternoon. We will be discussing BJT and JFET frequency response. But I will be dividing this topic into two. Okay, so I will be first discussing logarithms and decibels for our first video, and then I will be discussing frequency response in the other video because this topic is quite long. Okay, to start with, we will be discussing frequency effects. So last time we placed a load resistance and a series resistance to your transistor amplifier circuit, okay, and then we found out that their effect is they are lowering the gain. Okay, so the gain that we have discussed or computed on the topic is what we call the voltage gain or the mid-range voltage gain. Okay, why? Because that specific gain is working only on a specific frequency range. Okay, so when we place a signal or when we apply signal to your amplifier, we are not just applying an amplitude voltage of that gain. So we are also very particular with the frequency of the signal that we are applying. So why are we doing that? Because your signal has a frequency and has an amplitude. So the specific voltage gain of your amplifier will be will be functioning only at a specific given frequency range. So that is the frequency effect. Okay, so what will cause that frequency effect? So we will be discussing that in our topic. But for today, I will just be introducing you to a basic, okay, or a review topic regarding logarithms and decibels, which will be very useful once we discuss the frequency effect on our next video. Okay, so we have basically two types of amplifiers. So we have the AC amplifiers and then we have the DC amplifiers. Okay, so this AC and DC has something to do with the frequency. So when we say AC amplifiers, the voltage gain decreases when your input frequency is either too low or too high. So that means when we have a too low or a too high frequency, it will only a function. These AC amplifiers will only function at a certain given frequency range. Okay, so whereas a DC amplifier has a voltage gain all the way down to zero frequency. Okay, so it starts with the 0 hertz, which we consider as DC, up to a certain cutoff frequency. Okay, so an AC amplifier, it has a low and higher frequency range, whereas DC amplifier tends to start at zero or the DC 0 hertz or the DC range up to a certain cutoff frequency. Okay, so when we say decibels, okay, so this is used to describe the decrease in voltage gain. So we can specify the decrease in the voltage gain in terms of decibels. Okay, so bode plot, this is used to graph the response of an amplifier. Okay, so this is a frequency response of an amplifier. So what do we mean by frequency response? Frequency response is the graph of the amplifier's gain versus the frequency. Okay, usually this is your gain. So your gain at mid-band. Okay, so this is the gain that we are computing from our previous discussions. Okay, so usually we can express this as a unitless factor. Okay, so you have voltage output versus input voltage, or we can express this later in terms of decibels. So we're going to find out the the importance of expressing this in decibels, especially when we are talking about very, very high gain values. Okay, so at the y-axis, we're talking about the gain. So this is your loaded voltage gain. So this is your gain, what you say, at mid-range or at mid-band. Okay, and at the x-axis or at the horizontal axis, we have here your frequency. Okay, so as you can see, this voltage gain here, the one that we have solved, is flat or constant at a specific frequency range. But once it reaches a certain frequency, the tendency is to lower down its value. As once it reaches a certain frequency, it lowers a certain value. Okay, so at this two cutoff frequency, your voltage gain becomes 70.7% or 0.707 of your AV at mid-band. So we will be explaining that one by one. Okay, so what causes this one? Okay, what causes the frequency response? So at the higher frequency range, usually these are made up of what we call capacitance reactances. Okay, intercapacitive reactances. As you can see, it is in a form of a dotted lines. So that means it really is not made up of a component that you borrow in the laboratory. Okay, so it is within the transistor itself. So your transistor has intercapacitance reactances or intercapacitances that greatly affects your frequency response. And also, when we're doing circuit, we always have a ground. So we always place one wire at a certain point and then the other one is in the ground. So we do not know, okay, we're not aware of this, we're not very aware of this, but we produce what we call stray wiring capacitances, okay? Because if you can recall, a capacitance is produced when you have two parallel plates and between that you have an insulator. So an insulator can be in the form of an air. Okay, so we have one wire here and then you have a ground here. So this can serve as your parallel plates and then we form as three wiring capacitances. We didn't place any capacitors on the circuit, but uh, we're unaware that we have indeed created what we call this stray wiring capacitance. And these two here will play a great role in the frequency response of our amplifier. Okay, so the middle range of frequencies, okay, so we call that your mid-range, okay, so mid-range of frequencies, the voltage gain is maximum or at normal operation. So what we have solved in your previous amplifier circuit, so the voltage gain is equal to that value once you are in the middle range or in the mid-range of frequencies. Okay, so at low frequency, lower than the mid-range frequencies, your voltage gain tend to decrease. Okay, so what causes the decrease? So voltage gain decreases because the coupling and the bypass capacitors no longer act like short circuits. Okay, so the main considerations or the main factors that will affect your lower frequency are your coupling and your bypass capacitors. So in our previous discussions, we just say that your capacitors are shorted. Okay, at AC, your capacitors are shorted, but in fact, they will be shorted only at a certain specific frequency. If we do not reach that specific frequency, your capacitor is not automatically shorted. Okay, so the low frequency range will be based or will be dependent on your bypass and your coupling capacitors. Okay, how about the high frequencies? So also at high frequencies above the mid-range frequencies, your voltage gain again tends to decrease. Okay, but this time it is no longer because of the coupling and bypass capacitor, because once we reach their frequencies, okay, automatically they are already short circuit. Okay, so which will cause now your high frequencies. Okay, so the decrease at high frequencies. So this is due to the internal capacitances across your transistor junctions, the one that I've explained a while ago, and due to the stray wiring capacitance because of your wiring. Okay, so you might be the wiring really plays a very vital role in your circuit connection. So you might say, we're using the same components, we're using the same circuit design, we're using the same schematic diagram, but how come that my classmates or the other groups, they have a nicer output? Maybe because of how they place the wiring in their circuits, okay, in their PCB or in their simulations, okay? So because your wiring plays also a vital role in your circuit. Okay, so we have this lower frequencies and at upper or higher frequency, we call them cut-off frequencies. Okay, so cut-off frequencies, that those are the frequencies at which the voltage gain equals 0.707 of its maximum value. Later, we will be discussing why 0.707. So where did this 0.707 came from? Okay, so but now let's just accept that at cutoff frequencies, your voltage gain is equal to 0.707 of your maximum value. So where is the maximum value? The maximum value is at mid-range, okay? And at cutoff, it is 0.707. Now, below the cutoff and above the cutoff, it is much lower than 0.707 of your maximum values. Okay? So, usually, we call those cutoff frequencies as F1 and F2. Okay? F1 is your lower cutoff frequency and F2 is your upper cutoff frequency. Okay, so there are many names being associated with the cutoff frequencies. They can also be called as breakdown frequencies, corner frequencies, or much popular name also is referred to as half power frequencies. Okay, so why half power frequencies? Because at this cutoff frequency, your output power is just equivalent to half. Okay, half the output power at the midband. Okay, so how do we explain that? Power, okay, so power is given by, okay, power is given by VO squared or V squared divided by R. Okay, so output power at mid-band is equivalent to VO squared all over R. Okay, so that is at mid-band. Okay, so we can write VO mid, okay, equivalent to AV mid times VI. So if you're going to remember our loaded voltage gain, your loaded voltage gain at mid-band is equivalent to VO all over VI. So multiplying VI by V mid, that is your VO. Okay, so we have here AV mid multiplied by VI. So why did I place an absolute value? Because especially when we are talking about common emitter configurations, your voltage gain is always in terms of is negative. Okay, so we are not going to consider the negative sign. That's why we placed an absolute value there. Okay, so at certain cutoff frequency, so this is at the power output at midband. What will be the power at cutoff? However, at cutoff, your gain is equivalent to 0.707 of your AV mid. Okay, so we get square of that. So we square that. That will give you 0.707 squared, that will give you 0.5 of AV mid all over VI. So this AV mid all over VI is your PO at midband. Okay, so therefore at cutoff, that is equivalent to 50% of your power at midband. So if your output power, for example, is 10 watts, at these two cutoff frequencies, your power is just 5 watts. Okay, not equivalent to 10 watts anymore. That's why your cutoff frequencies or your F1 and F2 are also called half power frequencies. So this is the explanation for that. Okay, so at mid-band of an amplifier, so these are the band of frequencies between 10 times F1 and zero point 0.1 of F2. Okay, so the voltage gain of the amplifier is approximately maximum, and that is your AV mid. So this is what we solved in our previous topic. Okay, outside the midband, this becomes 1 plus F1 all over F. Okay, so this is the lower cutoff divided by any frequency below your F1 squared, okay? And then we have here 1 plus F all over F2. So this is your any frequency above your upper cutoff frequency F2. Okay? So we have here a term dominant capacitor. I will be explaining the term dominant capacitor once we discuss each capacitors in the bypass and the coupling capacitor. Okay? But anyway, among those three capacitors, we have one bypass capacitor and two coupling capacitors. Among the three capacitors, okay, only one capacitor will serve as or will dictate your low cutoff frequency. And that capacitor is what we call the dominant capacitor. Okay, so one that is more important. Although they are all important, okay, but one is more important than all others in determining the cutoff frequency. So I will be going to this later, okay? So once we discuss how to determine the cutoff frequency. But anyway, this is just the definition. Okay, so at mid-band, your voltage gain is equivalent to AV mid. Okay, that is your normal voltage gain. Below mid-band, okay, so that the voltage gain will be equivalent to AV mid. So this one, divide by 1 plus F1 all over F. F1 is your cutoff frequency, lower cutoff frequency. F is any value lower than your cutoff frequency. Okay, so you can see, so this is lower, so that means this parameter here will give you a value which is greater than 1. Okay, so if this is greater than 1, you square it, you add 1, then we get the square root. So we have here a denominator which is of greater value. So if you divide AV mid by a value which is greater than 1, technically speaking, the voltage gain will really decrease. Okay, so it will cause a decrease in your original voltage gain. The same is true with this. Okay, so if we have an F which is much, much greater than your upper cutoff frequency, again, this will give us a value which is greater than 1, which will give us a denominator which is greater than 1, and which can decrease the value of your voltage gain. Okay, but if your F here, okay, if your F here is lesser than 1, okay, is greater than F1, so this will not give us a very, very high value. So therefore, it will not affect your AV mid. Okay, so your F here must be lower than your F1, and your F here must be greater than your F2. Okay, because your F1 and F2 are your cutoff frequencies. So this is the response of an AC amplifier. Okay, so an AC amplifier has two cutoff frequencies, the lower cutoff frequency and the upper cutoff frequency. For a DC amplifier, the frequency response will look like this. Okay, so a designer can use a direct coupling between amplifier stages. So what do we mean by a direct coupling? We will not be using a capacitor, a coupling capacitor, whereas we're going to make use of a direct wiring. So in that case, there will be no capacitor that will dictate the output or the lower cutoff frequency. So in that case, so a designer can use direct coupling between amplifier stages. So this allows the circuit to amplify all the way down to 0 hertz. So therefore, from 0, since there will be no dominating capacitor that will dictate what will be your lower cutoff frequency, we will be starting from 0. So it will be you are going to amplify up to a certain upper cutoff frequency, because the upper cutoff frequency is dependent on the type of transistor that you are using and on the wiring on your circuit parameters. So therefore, you still have your upper cutoff frequency. So for DC amplifier, it's just your F2 that is being taken into considerations. Whereas for AC amplifiers, you have your F1 and your F2. So the two most important characteristics for a DC amplifier now is your AV mid and your F2. Okay? So DC amplifiers are more widely used than AC amplifiers because most amplifiers are now designed with op amps. Okay? Instead of discrete transistors. And op amps class are considered as DC amplifiers. Okay? So in your final period, we will be discussing operational amplifiers. So therefore, for once it reaches your F2, once it reaches its upper cutoff frequency, again the gain will decrease. Okay, and the decrease in your gain will be based on the frequency that is greater than your F2. So between mid-band and cutoff, okay, so this is, if this is our mid-band, automatically we are going to have a decrease in your voltage gain. So we are experiencing, or we can expect a decrease in your voltage gain. Okay? So we have here an example. So the figure shows an AC amplifier. So that means since we have an AC amplifier, we have a lower cutoff and an upper cutoff frequency. So with a mid-band voltage gain of 200. So as long as your frequency is within F1 and F2, okay, so we are said to experience a voltage gain equivalent to 200. Okay, if the cutoff frequencies are 20 Hz and 20 kilohertz, what does the frequency response looks like? What is the voltage gain if the input is 5 Hz? Okay, considering that 5 Hz is lower than 20 Hz, and if it is 200 kilohertz, considering that your 200 kilohertz is greater than the upper cutoff, which is 20 kilohertz. Okay, so the frequency response will look like this. So how do you draw the frequency response? So as we mentioned earlier, your frequency response is the graph showing your voltage gain with respect to your frequency. Okay, so our voltage gain at mid-band, okay, so it is between your lower cutoff and your upper cutoff. So this is equivalent to 200. Okay, now, this is your lower cutoff frequency, which is 20 Hertz. This is your F1. And this is 20 kilohertz. This is your F2. At 20 Hertz and 20 kilohertz, this is equivalent to 0.707 of your AV mid. So what is 0.707 of 200? So 200 multiplied by 707, we will be having 141.4. Okay, so we have here what happens. So this is the frequency response. So every time you are asked to draw the frequency response of an AC amplifier, it will really looks like this. Okay, so the only thing that will change are the values of the cutoff frequency and of course the value of your gain here. Okay, now, what happens if we have a frequency which is lower than 20 hertz? Okay, so in the example, we have here 5 hertz. So if it is lower than 5 hertz, what will happen? So we have just to apply that to our formula. Okay, so we have here 200, which is your AV mid, divided by 1 plus. You have here 20, which is your F1, divided by 5. Okay, so squared. So that will give you 48.51. So see, from 200, our gain was decreased to 48.51. That is when you use a signal that is not within your F1 and your F2. And if you do that, if you place a signal, okay, you get a signal generator, and then you get a specific amplitude, and then you get the frequency, and then you set your frequency to 5 hertz, and this is the type of amplifier that you build, you cannot maximize it because you cannot get the voltage gain that you really designed. So you designed for a 200 gain, and yet you can settle you just settle for 48.51. So that means, class, that in this type of amplifier, you do not use 5 hertz. Okay, so if your signal is 5 hertz, then you design another amplifier that is working at 5 hertz. So this specific amplifier here is just working between 20 hertz and 20 kilohertz. So if you plan to use 25 hertz, then this is not the amplifier for you. So that's the meaning of that. It's not just that you're just placing any signal. So it has something to do with the frequency of the signal that you are going to amplify. Likewise, if we choose 200 and 200 is not within the design range because it is just up to 20 kilohertz, what will happen? So substituting that into your formula, okay, substituting that into your formula, you will just get a gain that is equal to 19.9. And that means this is very, very low compared to your original design, which is 200. So what does that mean? So do not use a 200 kilohertz signal in this amplifier because it cannot amplify this specific frequency. So it's not just that you're going to place a signal and it will be amplified by 200 times. It will only be amplified by 200 times if your signal is within that F1 and F2 frequency range. So that's the meaning of that example. Okay? So we have here another example. The figure shows a 741C. So 741 is a type of an operational amplifier. So as I've mentioned earlier, an operational amplifier is a DC amplifier. Okay, so a 741C, an op-amp with a mid-band voltage gain of 100,000 if F2 is 10 hertz. What does the frequency response look like? So all you have to do is to draw the frequency response. Okay, so how does the frequency response look like? So since it is a DC amplifier, so it will start at 0. So starting 0, it will get a 100,000 gain, okay, up to a certain cutoff frequency. So at 10 hertz, its gain will definitely go down to 70,700. So that is your 0.707 point. Okay, and beyond 10 hertz, likewise, your gain is starting to decrease. So this is an example of the frequency response of a DC amplifier. So the difference is that a DC amplifier starts at 0 and ends at a certain upper cutoff frequency. Okay? So that's the difference between a DC and an AC amplifier. Okay, so we have here a decibel. Okay, so decibel power gain. So decibels, this is a useful method for describing frequency response. Okay, let us first have a review of logarithms. Okay, so in your lower mathematics, you have discussed logarithms. Okay, so there are two basic logarithms. We have the natural logarithms, wherein in your calculator, it is your ln, right? So in your calculator, so my calculator is quite old. So this is your ln. So your base is e, okay? And then your logarithm, natural logarithm, your base is 10. Okay. So we have here your logarithm is expressed as 10. X is equal to 10 raised to y. So if we wanted to solve for y, so it becomes log to the base 10 of x, which is equal to log of x. Okay, so you can have several what you call this bases. So you can have base 2, you can have base 5 or base 8, but we have to convert this, or you have to relate this to base 10 because in our calculator you only have base 10, which is your common logarithm, or ln, or the natural logarithm. Okay, so y is the logarithm or exponent of 10 that gives the value of your x. Okay, so using your calculator that has a common logarithm function, I want you to compute for the values of this. Okay, so all you have to do is to press lang naman your calculator. Okay? So, I don't know what your format for your calculator is, but for my high-tech calculator, so if I write here logarit at 10, then all I have to do is to press log. So, I have here 1. Okay? So, if I have 100 and then I press log, I have here 2. Okay, so you have your 1,000 and then I press log, I have here 3. So as you can see, your numbers here 10 to 100 to 1,000. Okay, so they decreased times how many times, but yet their logarithm value or their decibel value is just 1, 2, and 3. So they are just increasing 1, 2 by a factor of 1. Okay, so you can just count your zero. So 1 0 times uh 10, you have 1 0, so that is 1, 2 zeros, that is 2, 3 zeros, that will give you 3. Okay, so this is the same. So the only difference here, class, is you get a negative value. Okay, so we have here the answers na. So in here, you just get a negative value here. Okay, so this has positive value. It's increasing. Okay, so as x increases or decreases by a factor of 10, y only increases or decreases by a factor of 1. Okay, so imagine, and this is, you just have to place a negative sign here. Okay, so if you're going to place that in decibel, all you have to do is to multiply that by 10. Okay, so your power gain is defined as the output power divided by the input power. Okay, so power gain, this is the absolute power gain. So this is P out all over P in. Your absolute power gain is 10 multiplied by the logarithm of your absolute power gain. So as you can see, if our examples are 100, 100 million, so we have here 100, you have here 100 million, you have here 1,000, and you have here 100,000. That will only give you 20 dB, 80 dB, 30 dB, and 50 dB. So we have eliminated the number of zeros. Okay, so it's very difficult, or it's very hard, complicated to write many zeros. Okay, so instead of writing 8 zeros here, for example, it is easier just to write 80 dB. Okay? So, as you can see, all you have to do is to count the number of zeros and then multiply it by 10. So, you get 20 dB. You count the number of zeros, you have 8, multiplied it by 10, you get 80 dB, and so on. Okay? So, these are examples. So, these power gains are in its absolute form, and these power gains are in its decibel form. So, if we're going to draw a graph, if you're going to draw a frequency response, and then you are graphing you are placing on a graph several thousands or numbers of zeros, it is very very difficult for us to write those numbers of zeros. So it is simpler if we're going to express them in terms of decibels. Okay? So, decibel power gain are often used on data sheets to specify power gain of devices. Okay? So, instead of writing in the data sheet that the power gain of this amplifier is 100 million, so it's more technical, or it's nicer to write 80 dB instead. Okay? So we have here the two useful properties of decibel power gain. Okay? So each time the ordinary power gain increases or decreases by a factor of 2, the power gain increases or decreases by 3 dB. Okay, so later on we will be defining what power of 2 is that. So each time the ordinary power gain increases or decreases by a factor of 10, Okay, the decibel power gain increases or decreases by 10 dB likewise. Okay, so you may try this. Okay, so while listening to the video, you may try this one. Okay, so let us see. In this example, we are trying to increase your ordinary gain by a factor of 2. So we started with 1, 2, 4, and 8. So if we're going to look at that, we will be starting with, okay, so we will be starting with, so we will be starting with 0 dB, okay, from 1, and then 3 dB, so you try it, you have 6 dB and 9 dB. So every time, so if this is 16, so we are already predicting that the answer there is 12 dB. Likewise, if you are having, or if you are dividing this by 2, you're getting the same um plus 3, but this time we have a negative sign. Okay, so when you have a negative sign, that means your output, or the output or the numerator is lesser than the denominator. So in this case, the numerator is greater than the denominator because you have a gain in that case. And it's negative if you don't have a gain. So we call that your attenuation, okay, or a decrease. Okay, so kindly try this, okay, so that you can be familiar with with doing this type of computations using your calculators. Okay, now, how about decibel gain? So your decibel gain or voltage gain, the output voltage is divided by the input voltage. So this is our representation for the voltage gain. So we will be making use of voltage gain more compared with the power gain, because in the frequency response, we are actually getting the graph of the voltage gain with respect to the frequency. Okay, so your decibel voltage gain is equivalent to 20 logarithm of your voltage gain. So how did this happen? So originally, class, your decibel was designed for powers, really. But we can express powers in terms of voltage. So how do you do that? Powers in terms of voltage. Ah, I'm not yet done. Sorry. Okay, so this is a factor of 2. So another useful properties of decibel power gain is each time the ordinary power gain decreases or increases by a factor of 10, the decibel power gain decreases likewise by 10 dB. So in this example, you have 1, 10, 100, and 1,000. So you are increasing by a factor of 10. You're multiplying this by 10. And then this is you're dividing this by 10. Okay? So we can have this value. So as you can see, every time you do that, okay, so you have 1, that is 0 dB. So 0 dB because your numerator is equal to the denominator. That means you don't have a gain. You also don't have a loss because your numerator is just equal to the denominator. So therefore, you cannot say if it is positive or negative, because positive if you have a gain, negative if you have a loss. So if you have 1 equal, so that will give you a 0 dB. Okay, so increasing this by a factor of 10, as you can see, you're just having or just adding 10. Okay, and decreasing it by a factor of 10, the same but with a negative sign. That means you have a loss. In here, you have a gain. 0, that means you neither loss or you don't have a gain nor a loss. Okay? So, going back to the voltage gain, how did we get the 20 dB? So, we just express. Okay? So, what is your voltage gain? Okay, in terms of what is your power in terms of voltage gain? So in terms of power, it is VO squared all over R. Okay, so power expressed as a voltage is equivalent to V out squared or VO squared divided by R, okay? And then you have VI. So power, this is output voltage divided by input voltage. So this is in output power divided by output power. So for maximum power transfer, we say that we make use of the same impedance or same resistance both at the input side and at the output side. Okay, so canceling your R, that will give you VO divide by VI, which is your voltage gain, and then you have 2. So loss of logarithm, if you have an exponent, we just have to multiply this with this one. So they have 2 here multiplied by 10. So we get 20 here. So 20 logarithm of AV. Okay? So we have an example there. So for a voltage gain equivalent to 100,000, we just write it as 100. For a voltage gain equivalent to 100, so this is 40 dB. And for a voltage gain equivalent to 100 million, so that is equivalent to 160 dB. Okay? So we have your basic rules for voltage gain. Every time the voltage gain increases or decreases by a factor of 2, this time it is increased or decreased by 6 dB. So for power, it is 3 dB because we just have to multiply your logarithm equivalent by 10. So this time for voltage, you have to add or subtract 6 dB. Okay, because we have 20 instead of 10. And likewise, every time you increase your voltage gain or decrease your voltage gain by a factor of 10, so the decibel voltage gain likewise increases or decreases by a factor of 20 dB. So in power gain, it is 10 dB. So for voltage gain, it is equivalent to 20 dB. Okay? So for cascaded stages, so we have discussed, okay, we have discussed cascaded stages from our previous video. So the total voltage gain of the two-stage amplifier is the product of the individual voltage gain. So we have here your AV total is equal to the voltage gain of your first stage multiplied by the voltage gain of your second stage. So for example, what is the total voltage gain if the voltage gain of the first stage is 100 and the voltage gain of the of stage 2 is 50? So very simple. All you have to do is just to multiply it by 100 for the first stage and 50 for the second stage. That will give you a total voltage gain of 5,000. So what is the effect of cascading your amplifier circuits? So cascading your amplifier circuits technically what increases your voltage gain because you're multiplying two two high gains system. So therefore that will give you 5,000. That means your input will be amplified 5,000 times, okay, at the output side. Okay, now, what if if your voltage gain are in terms of decibels? So it says here, the decibel voltage gain, okay, can be written as 20 logarithm of AV1 and AV2. So if you're going to remember our rules of logarithm, okay, so if you have a product, okay, so this will just as if you are adding them separately. So that will give you 20 log of AV1 plus 20 log of AV2. So this is from the laws of logarithm for multiplier, for multiplication for a product, okay, products of logarithm. So it can be rewritten as your AV1 in terms of decibel plus AV2 in terms of decibel. Okay, so if your voltage gain now are in terms of decibels, no need to multiply them. You just have to what? You just have to add them. Okay? So therefore, the total decibel voltage gain of two cascaded stages equals the sum of the individual decibel voltage gain. So we are now using the additive property of your decibel gain. So it's easier to add than to multiply. Okay? So if you have your ordinary voltage gain, you multiply the gain of each stage. But if your stages are in terms of decibels, you simply add them. Okay, so we have here an example. What is the total voltage gain in the figure? Express this in terms of decibels. Next, calculate the decibel voltage gain of each stage and the total decibel voltage gain. Okay. So for this example, we have here, first is we solve for the total the voltage gain. Express this in terms of decibel. So the total voltage gain is the product. Okay? So AV1 times AV2. So that will give you 100 times 200. So that will give you 20,000. Okay, so expressing that in decibels, so we use 20 here because that is a voltage, okay? So 20 logarithm of 20,000. So that will give you 86 dB. Okay, so this is 86 dB. So another is we're going to get the decibel of each stage. So getting the decibel value of this stage, this is 40 dB and this is equivalent to 46 dB. Okay? And then adding them, we will just get the same answer, which is 86 dB. So in this case, we have observed. Look, did you notice this one? So, logarithm of 100 is 40 dB. Okay, so what do? You just count this, you have 2, and then multiply by 20, so you get 40 dB. Okay, so 100 is what? 200 is 2 times 100. So we multiply this. And it says that if you multiply this by 2, okay, by a factor of 2, you will have a plus 6 dB. So from 40 dB, you have 46 dB. Okay, so we add 6 dB. Why? Because we double your 100 and make it 200. So that's why we had here 46 dB. And adding the 2, we got 46 dB. Okay, so it's either you use this one or you get their decibels and then you just simply add them. You get the same answer. Okay? So what is the concept of impedance matching? So this shows a system that is not impedance match. And this shows a system that is impedance match. So usually, we have a load resistance, okay? We have an R output impedance, we have an input impedance, and we have, this is your series, this is your source resistance. Okay, so we use generator here, so we just use RG here. So when your system is not impedance matched, so these four resistances here, these four impedances here, they are not equal. Okay, so they are not equal. It says that impedance matching is very important. So what do we mean by impedance matching? Your internal resistance here, your output impedance here, your source resistance here, and our load resistance here, they are all the same values. So if they are all the same values, it is said to be the system is impedance matched. Okay, so all impedances are matched for many communication systems. So you can detect or you can determine what type of communication system is that just by knowing what is the impedance. Okay, so why impedance matching? Why is it important? Because it produces maximum power transfer. Okay, so some popular standard resistance or impedance values are of the following. So for microwave systems, you use the impedance equivalent to 50 ohms. Okay, so for television, it's either 75 ohms or 300 ohms depending on what type of connections you are using. So if you are using coaxial cable, that is 75 ohms, but if you are using the twin pair or the flat pair of wires, that is equivalent to 300 ohms. So if you will be buying, for example, at Ace Hardware, and then you will say the coaxial cable for a television, so that coaxial cable is has an impedance of 75 watts. Okay, or if you're going to connect extension phones at home. So for telephone systems, you are using an impedance of 600 ohms. Okay, so those are standard values. Even speakers have 4 ohms, 8 ohms, 16 ohms depending on their specific value. So that's the concept of impedance matching. It produces maximum power transfer. So the power gain equals the square of the voltage gain in any impedance matched system. Okay, so they are equal. Okay, so AP or the power gain, that is equal to the square of AV squared. Okay, but okay, when we have a decimal power gain, so just like what we did earlier, okay, we have here the decimal power gain equals the decibel voltage gain for any impedance match system. Okay, so this is equivalent to 10 log of PO all over PI, and this is equivalent to 20 log of VO all over VI, but their value are the same. Okay, so the values are the same. Okay, antilog. So what is antilog? Antilog is the inverse logarithm. So what for if we are given, for example, a value in decibel, and we wanted to get the ordinary power gain or the absolute power gain or the absolute um, voltage gain, we use the antilog. So in certain types of calculators, okay, so what you do is you just press shift and then log. So that is for anti-logarithm or anti-log. Okay, so that is the inverse of logarithm. So if we wanted to get the ordinary power gain, that is simply equivalent to anti-log of your decibel power gain divided by 10. And if you wanted to get the ordinary voltage gain, so we'll just get the anti-logarithm of decibel voltage gain divided by 20. Okay, so we have here an example. The figure, so this is an impedance match system. So why impedance? So probably this is a microwave system because their values are all 50 ohms. So as you can see, all of the impedances that you can see in the circuit or in the block diagrams are all equal to 50 ohms. So most probably this is a microwave. Okay, because for a microwave systems, it is equivalent to 50 ohms. Okay, so the figure shows an impedance match stages with R equal to 50 ohms. What is the total decibel gain? What is the total ordinary power gain? Okay, the total ordinary voltage gain, and what is the ordinary voltage gain of each stage. So each stages, we have 23 dB here, you have 36 dB, and we have 31 dB. Okay, so let us solve this problem. So for the total voltage gain, okay, since they are in terms of decibel, what do? We simply add them. So we simply add them, class. Okay, so the total voltage gain is equivalent to AV1 plus AV2 plus AV3. So that will give you AVT, which is equal to 90 dB. And since this is a impedance match system, we can say that the decibel voltage gain is equal to the decibel power gain. So decibel voltage gain is equal to 90 dB. Likewise, your power gain is equal to 90 dB also. But that doesn't mean that your voltage gain ordinary is equal to the power gain ordinary. Okay, but since they are equal because of the impedance match consideration, we can solve for your power gain. So the power gain is equal to 90 dB from there. Okay, so since they are equal, so 90 dB 10 log of AP. So what we don't know is this one. So we're going to get the concept of what? Anti-logarithm. Okay, so that will give you 90 divided by 10 anti-log. Okay, so 90 divided by 10 and then inverse logarithm. So that will give you what? 1 million. So imagine, your power gain is equivalent to 1 million. So which is easier to write? You have to write here 9 zeros, whereas here, all you have to do is to write 90 dB. Okay, so what's the other question? So this is your total decibel gain. This is your total decibel gain. What is the total ordinary power gain? So this is the total ordinary power gain. But you will just assume, or you will just make them equal if your system is impedance matched. Okay, if your system is not impedance matched, this will not apply. Okay, and then other one, what is the total ordinary voltage gain? Okay, so your total ordinary voltage gain is, since they are also equal, so we can also use 90 here, 20 log. So this time 20. Why? Because we're using voltage gain. So 90 divided by 20, anti-logarithm, you have here 31,623. So this is the ordinary voltage gain, and this is the ordinary power gain. So our consideration earlier is what? Your power gain is equal to the square of your voltage gain. So if you square 31,623, that will give us approximately equal to 1 million. Okay, so we just didn't get the exact value because we're rounding off, but it is approximately equal. So if you square this 31,623 and then you get you square that, you will get a value that is approximately equal to 1 million. Okay, so another solution in solving for this power gain is to get the ordinary gain for each stage. So the ordinary gain for each stage is 23 divided by 20, since this is a voltage gain antilog. So that will give you 14.1. This will give you 63.3 and 35.5. So I suggest you compute this at home. Okay, so you practice solving this using your calculator. And then what you do, if you have an ordinary voltage gain, to get the total voltage gain, we just multiply it. So multiplying this three, okay, so we have 14.1, 63.1, and 35.5, we get approximately 31,584, which is approximately equal to this one. Okay, we just didn't get the exact value because we're rounding off, but they are approximately equal. So it's either you use this, okay, and then you multiply, or you just get the anti-logarithm for you to get the absolute voltage gain for that specific problem. Okay, actually, class, the computation is very simple. The computations are very simple. So this is just a matter of addition, multiplication, and then the only addition of your logarithm. Okay? But logarithm and decibels, they're very important because we are minimizing the use of many zeros. So instead of writing many zeros, we just convert them into decibels. So that is why we make use of logarithms and decibels. Okay? So decibels above reference. Okay, so what do we mean by this? The milliwatt reference, this is used to indicate the power above 1 milliwatt or dBm. A way of comparing power to 1 milliwatt. Okay? So, when you have 1 milliwatt here, automatically, we are using an input or a reference value equivalent to 1 milliwatt or 1 millivolt. Okay? A volt reference, that means you're using 1 volt here. Okay? So, we have here an example. A data sheet says that the output of an amplifier is 24 dBm. What is the output power? Okay? So, we can solve for that. Okay, so your voltage power gain is in decibel is equivalent to 10 log of PO all over P in. So power in decibel is given by 24 dBm. So that is 10 log of 20 divided by 1 milliwatt. So why 1 milliwatt? Because we have here dBm. So the M here specifies that automatically we have 1 milliwatt here. Okay? So your PO now can be solved by 20 divided by 10, and then we get the anti-logarithm of this one, antilog, and then after getting the anti-logarithm, you multiply it by 1 milliwatt. So your output is equivalent to 251 milliwatts. That also explains why we have a positive value for 24 dBm. So why is this positive 24? Because as you can see, the output is greater than the input, which is 1 milliwatt. So every time your output is greater than your input, we expect a positive decibel. For the second example, given a microphone rating of negative 54.5 dBV, okay, what is the output voltage? So in this case now, we have a voltage gain which is equivalent to 20 logarithm of 420, VO all over VI. So we place here negative 54.5 dBV. So we can write that as 20 logarithm of VO divided by 1 volt. So the fact that we have here dBV, we have a reference voltage here equivalent to 1 volt. Okay? So in this case, we can solve for VO. And VO is equivalent to antilog of negative 54.5 dBV divided by 20 multiplied by 1 volt. And that will give you 1.88 millivolts. Okay, so when you press that in your calculator, you will really get a positive answer here, even though that is negative. But as you can see, the negative sign here signifies that this output voltage is less than our input voltage, which is equal to 1 volt. So 1 volt is greater than 1.88. So therefore, there was a decrease at the output. Since there was a decrease at the output, we have a negative dB. Okay? So, a positive dB, always remember, a positive dB means you have a gain. Okay? A negative dB means you have a loss. And when you have 0 dB, okay, your output is just equal to your input. So, it's neither gain nor loss. Okay? So, always remember that. So do you have a sit work here? Okay, so I will be placing what do you call this? Dropbox in our school book for this sit work number 2. Okay, so this is just an easy sit work. Okay, how about bode plots? So what do we mean by bode plots? Okay, so bode plots, this is a graph which uses decibels, okay? It can give more information about the amplifier's response outside the midband. Okay, so octave, this refers to doubling of frequency. Every time you go up 1 octave, you have doubled the frequency. So remember, earlier we said that every time you multiply by 2 your power, you have 3 dB, and every time you multiply by 2 your voltage, you have 6 dB. So in a more formal term or formal what do you call this name, we will be calling that octave. Okay, so every time you double your frequency or you double the so we say we increase 1 octave, 2 octaves. So that means you have multiplied by 2 times, so 2 octaves. Or we have you have lessen by 2 octaves. So that means you have 2 octaves lower or 1 octave lower. So that means double or double the frequency. So we that term is called octave. So if a factor of 10 is used instead of a factor of 2, so we call this naman decade. So let us say 500 is 1 decade above 50 hertz. Or 2 megahertz is 2 decades above 200 kilohertz. So that is about decades. So that means 50 times 10. So that will give you 500, or 2 kilohertz times how much is that? 2 megahertz. So 10. So 10 octaves. So 10 octaves lower than 2 megahertz is 200 kilohertz. Okay, so that's decade. So we have here linear plots. The spaces between the numbers are the same for all numbers. So we have here logarithmic scale. This compresses very large values and allows you to see over many decades. Because if we're talking about gigahertz or megahertz, for example, and then you're going to make use of linear scale, so how many lines we're going to make use of, right? But if we're going to make use of logarithmic scale, we can, okay, compress very large values and allows us to see over many decades. in frequency response, what we use is semi-logarithmic graph. Usually, this is a linear scale on the vertical axis, and that is usually our gain, and then at the logarithmic scale at the horizontal. So that is our frequency, because usually we are looking on a very, very wide range of frequency, so that we can accommodate that very, very large scale in frequency or range in frequency. We make use of semi-logarithmic graph. Okay? So this is your decibel voltage gain uh, versus frequency. So this is your AV mid. So this is in terms of, this is your AV or your voltage gain, and then this is your cutoff. So usually you have a negative 20 dB per decade. So you decrease 20 dB of the gain per decade, or after increasing. So 20, per decade decrease in F1 or per decade decrease in F2. Okay? So, this is your cutoff frequencies. So, starting at the cutoff frequency, so this is the real. But if we're going to look at the ideal, so starting at the cutoff, it will significantly decrease for about 20 dB, negative 20 dB per decade, or 6 dB per octave. Okay? Or 20 dB per decade, or again, negative 6 dB per octave. So the decibel gain is maximum in the middle band or in the mid band. At each cutoff, the decibel gain is down slightly from the maximum value. So that slightly is 0.707. So below F1, the decibel voltage gain decreases for about 20 dB per decade. And above F2, the decibel voltage gain decreases for about 20 dB per decade. Or we can use 6 dB per octave. Okay? So this is the ideal approximations. Ideal Bode plots, approximations that allows us to draw the frequency response of an amplifier quickly and easily. So for example, our gain is 40 dB. Okay, so upon reaching your first cutoff frequency, which is 1 kilohertz, 1 decade lower than 1 kilohertz is 100 hertz. So as you can see, from 40 at 100 hertz, this is already 20 dB. So it decreases 20 dB per decade. 1 decade again lower than 100 hertz, that is 10 hertz. So at 10 hertz, it is already 0 dB, because 20 dB less than 20 dB, that will give you 0 dB. The same is true at the upper cutoff. So what is 1 decade higher than 100 kilohertz? 1 decade higher than 100 kilohertz is 1 megahertz. At 1 megahertz, your original gain of 40 dB is down to 20 dB. And another 1 decade, so 1 decade above 1 megahertz is 10 megahertz, your decibel voltage gain is down to 0 dB. Okay. And at the cutoff frequency, so what are the cutoff frequencies for this? That is 1 kilohertz and 100 kilohertz. Between them, your gain is 40 dB. As long as your signal is within the 1 kilohertz to 100 kilohertz. So that is your ideal Bode plot. So, general frequency considerations for an RC coupled, that means you use capacitor to couple or to connect your input signal to your output signal, or to your amplifier, and your amplifier to the output signal. Usually, this is our curve. Okay? So, this is our frequency response. Okay? So, what causes the lower cutoff frequencies are your emitter, are your source capacitance, your output capacitance, and your bypass capacitance, your CE, your CS, and your CO, CC. Okay? And then, for the upper cutoff, these are made of the parasitic capacitances of your networks or your active devices, and your circuit, your ground, and your stray capacitances. Okay? So for transformer coupled, your frequency lower cutoff frequency is being made up of the transformer. Remember, your transformer is an inductor, and inductor also has a frequency, okay, in your circuit analysis. So inductors, they also have frequency. So therefore, the one which causes the low frequency and the high frequency response are the transformer in the form of a coil, okay? While for direct coupled, you see, you have no lower frequency response, just the upper frequency response, and that is because of your parasitic capacitances. So we're going to discuss this as we go on. Okay, so 0.707 of your AV mid, so these are fixed boundaries. Fixed boundaries of relatively high gain. Okay? So, F1 and F2, they're also called corner, cutoff, band, break, or half power frequencies. So, half power frequencies because your output, okay, is equivalent to at this half power frequencies is equivalent to 0.5 of your power at the output or at the midband. Okay? Your bandwidth is equivalent to F2 minus F1. So this is your pass band. Within that, okay, you're operating at a maximum voltage gain. So usually these are being used in communications, both audio and video. Okay? So the decibel plot and the logarithmic plot. So this is the normalized gain class, okay? Because if you're talking about it is decreasing, but if you're going to look at it as decreasing, but still it is on the upper side of your graph here, it looks like it still has a gain. So we cannot see the effect that it is decreasing because it is on the upper end. So what we do is we usually normalize. Okay, so we have here the normalized gain versus frequency plot. So in this case, we just divide your AV divided by AV mid. So that is equivalent to 20 logarithm of AV all over AV mid. But at mid band, this is equivalent to 1. Okay, so this is equivalent to 1 because at mid band, your AV is equal to AV mid. And then slightly, so this is 1, at 0.707 here, it drops. Okay, so it is 0.707 of your AV mid all over, AV all over AV mid. So the decibel plot of the normalized gain for low and high frequency regions, this is visualization of the broad system response. As you can see, if this is equal to 1, okay, any value of your of your gain which is equal to is equal to 1, that will give you 0 dB. So as you can see, class, you have here your 0 dB. So this is your mid band. And every time you are decreasing, okay, at 0.707, so if you're going to get the decibel for 0.707, that will give you negative 3 dB. So in this case, we can see that there is really a decrease compared to this upper side. So the normalized gain is just representing your frequency response below the zero level, because at mid-range, we can see that you have 0 dB and it is decreasing at negative 3 dB at your cutoff, and slowly decreasing of either 6 dB per octave or 10 dB per decade. So this is just the same. However, we express this in terms of the normalized gain. Okay, so phase plot for an RC coupled system, there is a 180 degrees phase shift between input and output signals at mid-band region. So at mid-band region, so you have here 180 degrees phase shift. At low frequencies, okay, your VO lags VI by an increased angle. And at high frequency, phase shifts drops below 180. So the 180 degrees phase shift for common emitter amplifiers is good for the mid-band region only. Okay, so it is above 180 degrees for low frequencies and it is below 180 degrees for what? High frequency signals. Okay? So, the low frequency analysis for both plot, we'll just explain that in our next video. Okay? So, for now, you have one sit work. So, I will be placing Dropbox for that sit work, and then we will be continuing our discussions on the next video. Okay? Thank you very much and God bless.